Okay, so let's work some examples with this, and I forgot to put my little vector signs here, so these need to go here and here. Let's work some examples with this and see what this center of mass stuff is telling us. All right, so the first thing is let's just rewrite the things that we know we know now. We have the total force acting on the system is going to give the uh, total acceleration of the center of mass. This is not. This is the acceleration. This is the center of mass acceleration. It's going to give that weighted by the mass of the total system, right? So this is a really amazing result. What it tells us is that if we know the forces acting on a body, um, and we don't need to know anything else to know how the center of that body is going to move. So as sort of an example that will make this make sense, let's say that we've got the sun here, okay, and over here we've got the earth, okay. Well, let me make that a little bit bigger so I can draw the pictures that I want. All right, so over here I've got the earth, and of course I know the force of gravity is being exerted on the Earth by the sun. It's being attracted to the sun. It's got a velocity. It's moving some direction this way. Some velocity here going this direction. But there's a whole lot of stuff going on the surface of the Earth and inside the Earth, right? So first of all, we've got the Earth is just rotating. So the Earth itself is rotating. But also we've got, like, you could have your hurricanes and stuff like that happening up here. You've got wind currents and stuff going over here. We've got volcanic explosions and stuff going on up here. There's oceans, there's magma, there's all kinds of stuff moving around in here. So this is an incredibly complicated system. There's all kinds of stuff going on, but all of those forces are internal. There's nothing happening outside of the Earth that all that commotion on the inside is changing the external forces acting on the body. And so because of that, we get to treat the Earth as if it were just a point particle with the entire mass of the Earth in one spot. That one spot is wherever the center of mass happens to be. By the way, the center of mass doesn't have to be dead center. It could be a little bit off. We'll give you some examples of that in just a second. So there's our Earth. It's got the entire mass there. It's got the same force acting on it, and we can calculate or figure out what its acceleration will be, and we can calculate what its orbit's going to be without needing to know any of this internal stuff that's going on. That's the beauty of this derivation that we just did, and that's the beauty of understanding what's going on with the center of mass. Now, here is where in archery things get a little bit confusing. This goes back to the discussion of FOC. So when we're talking about FOC of an arrow, so here's my arrow, very crudely drawn, but there it is. So there's my arrow with some veins on the back of it here, and so that's it. And we know that there is a central point here somewhere in the shaft. That's well, we'll just call it the center of the arrow. And then somewhere up here is the balance point, which is the center of mass. That's the center of mass of the arrow. The center of mass and the center of gravity are not necessarily the same thing, but they are in a uniform gravitational field, and for an arrow, the gravitational field is uniform. So where the balance point would be the center of mass of the arrow. Okay, so the question is, can changing the center of mass change where its location, moving the center of mass forward or moving the center of mass back, have an effect on penetration? That's a question that's asked. And some people have misinterpreted this F equals ma for the whole system, F equals ma, to answer that as no. They've basically said, we're going to learn that you can integrate this and get something called impulse. And what they say is that the center of mass, or the center of the FOC in the case of an arrow, doesn't appear in any of these equations, and therefore it's not going to have any effect. And I actually, when I first started thinking about FOC, this was one of the early mistakes that I made, just because I wasn't thinking about it deeply enough. I just kind of thought, wait, the center of mass moving forward, that's not going to have any effect on anything. That's not anything to worry about. Let me give you some examples of why that's not true and why the center of mass can have a major impact on the trajectory of the arrow as it's or even penetration depth as a possibility. So the simplest example is to imagine that you have, I don't know, like a satellite in space. Okay. So here's my satellite. This you're gonna have to excuse my very poor drawing, but here's my satellite floating through space, and it's on some trajectory like this. Okay, so it's moving through space this way. We're going to assume no forces are acting on it. There's actually gravity acting on it, amongst other things, but we're going to assume no forces acting on it just to make this extremely clear. And then what we're going to have is a detonation on the inside. So there's going to be an explosion. Big boom, right? And so what's going to happen is you're going to have pieces, these pieces flying off of it in various different directions, split and flying off in directions like this, and flying off this way and flying off that way. But what this tells us is all that explosion was internal. That happened inside. That was not an external force acting on the satellite. So even though it blew up and pieces went flying everywhere, if you know the center of mass of say this was our center of mass in this satellite, if it was moving this way before, you can guarantee that center of mass is still going to keep moving in that exact same location. Now, the pieces themselves will be flying out, but if you calculate the center of mass of those pieces, it will stay exactly on this course. It's going to keep moving exactly the way it was moving because there's no external forces acting on it, and no external forces. F equals ma, no external force, 0 means 0 acceleration. The center of mass is just going to keep moving the exact same way. Okay, so that's kind of the argument. The argument is it doesn't matter if the arrow's flexing back and forth. It doesn't matter any of that kind of stuff. It doesn't matter where the center of mass is. All you need to know is what the external force is acting on the arrow, and that will tell you the acceleration, and you can use that to figure out penetration. And that means that center of mass is not going to have any effect if it's in the back or in the front. It's still just going to keep moving on the trajectory that it's supposed to, given the external force. That is true. That is absolutely true. There's no, whether or not the center of mass is at the back of the satellite or at the front of the satellite or out here on one of the wings of the satellite or even not in the satellite at all. Maybe it's somewhere in space. The center of mass can be anywhere. It doesn't have to be in the actual object itself. That center of mass will still follow that trajectory regardless of where it is in the body. But the assumption there is that the forces don't depend on the center of mass. So this is, again, one of those things where you're making an assumption about how the forces are going to be. So let's do this exact same experiment, but let's not do this experiment now in space. Let's do the experiment in air. So what we're going to be looking at now is a glider. Okay, so we've got a glider here, big long wings sticking out this way. And it's got a center of mass somewhere up here, usually kind of forward of center, actually, because for stability in flight, you need the center of mass forward of center, and that center of mass is going to be following some trajectory. Now, if that center of mass if this thing were in outer space and there were no forces acting on it, then that center of mass would just keep moving regardless of what happens. But once again, we're going to detonate an explosion, and so here's our explosion. And particles, pieces of the jet are going to be flying around everywhere. There's a wing over there. There's a wing over here. There's a bit of the tail going this way. So stuff is just flying all over the place. And the question we have now is, does the center of mass change its trajectory? And the answer is yes, very, very much. The center of mass is the trajectory. This is the predicted trajectory. This is the real trajectory. Could be all kinds of wacky. It could go all over the place. Why? Because here the total force acting on the arrow, on the glider here, is the drag force. We've got a drag force acting on it. And here, as these particles are moving, these pieces of wings and other things are moving through the air, they all have drag forces acting on them. And if you add up those external drag forces, the drag forces before the the drag, let's call it drag 1, that's the drag before the explosion, and the drag after the explosion, we'll call that drag 2, are not equal to each other. So the center of mass is moving around and going all kinds of crazy place, completely different than our predicted center of mass, because the force has changed. And so if you have a center of mass in an arrow like this, yes, it is true that given the same external force, you don't need to know any where the center of mass location is. It's going to follow the same trajectory. It doesn't matter if it's at the back or if it's at the front. However, if the location of the center of mass has an effect on the shape of the arrow, then that will change the external forces, and the change in external forces will change the acceleration. The change in acceleration will change the penetration depth. So if moving the center of mass around causes, say, the flexing in the arrow to be different on impact, for, say, a center of mass that's very high in front of center versus one that's in back of center, if the compressive forces on the shaft changes depending on the location of the center of mass on impact, then that can very easily have an effect on penetration for that arrow. And I actually did an entire video on this. It's a long video. You can go read it, or excuse me, watch it yourself, and you'll see that I actually derived the equations that show the different compressive forces acting on the arrow as a function of, really, it's a function of the broadhead mass to the arrow shaft mass, which the center of mass is sort of a parameter that you can use to describe that ratio. But it's really how much of the mass is in the shaft and how much of it is in the head. And the more in the head and the less in the shaft, the less the compressive forces acting on the shaft at impact, the less the shaft will flex. But the more of the mass is in the shaft and the less in the head, the shaft will experience greater compressive forces, will flex more. And as it's going through the animal, if we've established a vibration in the shaft because of that flexion, that could very largely affect the forces acting on the arrow and change pretty dramatically the acceleration. So there is certainly scientific and physics reason for FOC being important in penetration. Now, I'm not saying it is. Don't get me wrong. I'm saying that there is a mechanism by which it could be important. So just throwing out FOC as not being relevant because it doesn't obey physics is incorrect.